Okay, finally in chapter 5. So chapter 5 is going to cover the most common inference that we can do for numerical data. So it's important that we realize that we're talking about numerical data, right? Because then we have, we can look at the histogram and figure out the distribution, and usually we're going to analyze the mean, right? And so for most of these, we're analyzing the mean. And I'm going to put means in brackets because we're going to start, of course, with just looking at one sample mean and comparing it to some number, very much like we did in chapter 4 with just basically one change, but stay tuned. And then we're going to move to talking about, okay, what if I've collected 2 samples and I want to compare their means? Right? So we also need to be able to do that. And that's kind of more common that we do. So, so we're kind of building up to that. But it's good to have a kind of the broad strokes of all of these. Okay, so this is part 1. I've started, it's kind of like, the textbook just goes straight in to introduce the one sample mean with the t-distribution. But what I decided to do was I just wanted to introduce the t-distribution, just talk about what makes it different. And then we'll be able to move a little bit quicker through the next few sections, just knowing and having a good idea about the t-distribution. So the t-distribution is very much like the Z distribution with one difference, okay? But the t-distribution is the distribution that we're going to use, okay? So in real life, this is the distribution that we use. And of course, I'm gonna talk about that, blah, 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 blah. And so, oh, kind of cramped here. Yeah, so we're just going to introduce the t-distribution, talk about what is it, what does it look like, why is it different from the Z distribution. So here we go. Well, first let's do a little compare and contrast here. Just bring this up here. So we've talked about the Z distribution. We use the Z distribution in chapter 3 and then in chapter 4, but this, now we're gonna leave it kind of behind and then we get to use it again in chapter 6. So, but kind of in a different context. So we will use the Z distribution, but we're gonna leave this version of the Z distribution behind. In general, right, both of these Z and T are called test statistics, right? So they do the same thing, which is what? They tell us how far our observed value is from the hypothesized value, right? So in kind of broad terms here, that they're both test statistics, and they tell us how far an observed, or maybe I'll just say our X bar is from the hypothesized mean. Oops. Hypothesized mean, which is, of course, mu naught. Okay. We introduced that in chapter 4, but of course, we're going to see it again here. So this mu naught and this mu naught, they're all the same. This X bar is still the sample mean for both of these, and N is, of course, the sample size for both of these. So the only difference here, and we noticed this last, not last day, for me, last day, But we notice this, right? The real difference, or the only difference between a Z and a T, is whether we know sigma or not. So usually what we call these is Z distribution is for one sample mean with sigma known. Whereas a T distribution, we use it for one sample mean with sigma unknown, okay? Because we're having to use the sample standard deviation instead of the population standard deviation, right? And so we use Z for one sample mean, oops, sigma known problems. And we use T for one sample mean sigma unknown problems. Okay. I want you to just take a second here, because this confuses a lot of people. You know, you've managed to remember that sigma is the standard deviation, but what you need to remind yourself of is that it's the population standard deviation, right? And so we still have a standard deviation, S, but we have the sample standard deviation, right? And so when we say sigma known, we mean, do we know the population standard deviation? And when we say, oh, we sigma unknown, right? So here, sigma unknown, then we're saying, okay, well, I don't know the population standard deviation, but I do, of course, have my sample standard deviation. So I use that instead. If we just take a moment, and I think I've mentioned it maybe briefly last day, but it's worth mentioning again how silly it is to assume that we would know the population standard deviation, right? Because what would that mean? It would mean that we would have collected the entire population, calculated its standard deviation, and then we just didn't do anything else with that data, such as figure out what the mean is, for example, right? So now we're trying to hypothesize, what do you think the mean is? Oh, I don't know. But I have the population standard deviation. No, that doesn't happen, right? So in real life, we're gonna have to use a T distribution, which is fine. But it introduces this kind of I want to say a volatility, but that's a little harsh. It introduces these two layers of variability. And so remember last day we said our X bar, okay, depending on our sample size N, X bar is either going to be really close and reliable to our population mean if we have a large sample size. And then we said, well, if we have a small sample size, then our sample mean is less reliable, meaning it might not be as close to the population mean as we want it to be, right? And so now when I'm talking about, okay, so depending on the sample size, right, the sample standard deviation will also have that variability, right? So the sample standard deviation, as we increase our sample size, of course, our sample standard deviation will also get more stable, right? And more reliable and closer to the population standard deviation. But now we have this, and I always try to do it, but I can never do it. You know, when you rub your stomach and pat your head. Hey, I think I'm like doing it. Well, you can't really see. Well, okay, never mind. So it becomes like, okay, so here's the mean, and it's kind of like changing depending on the sample size. And now also the standard deviation is also changing depending on the sample size. And so that's why the T distribution is a little bit different. And that is the only reason that we use Z to start off with. And that's why I call it the training wheels. But IRL, in real life, right, we're going to use the T distribution because the Z distribution, that's not going to happen. Okay. So let's grab some more here. Hope it copied. Nice. Oh, too big. Right, and so here's what I was saying before. So we're always going to be given a standard deviation. So the question is, where did the standard deviation come from? Right, and I know it's going to happen again because it is so confusing, and I remember being confused by it too. And I'm gonna get, you know, late night texts going, how's this sigma unknown? We have a standard deviation. Yes, you do, but sigma is the population standard deviation, and you only have the sample standard deviation, right? So really take a moment to kind of let that sink in. So where did the standard deviation come from? If it came from the population, usually the information kind of is given in a specific way to indicate that, hey, this is the standard deviation for the entire population. So it would say something like blah, blah, blah follows a normal distribution with a mean of this and a standard deviation of this. Okay, so then you're given the population standard deviation. Or you could say something, or it could say something like, assume the standard deviation for all blank is blank. Okay, so as soon as you're talking about the standard deviation for all of anything, that is the population, right? Whereas more reasonably, right, the sample, so if it came from just the sample, so a sigma unknown, then the information would be given as blah, blah, blah. You took a sample and found the mean to be this and the standard deviation to be this. So then by context, you can see that this standard deviation came from the sample, right? Come from the sample, right? And so that means you are only dealing with a sample standard deviation and not a population standard deviation. Oops. Okay. So, like I said, in real world scenarios, we'll never know sigma because that seems weird, right? So for analyzing one sample mean in real life applications, we must use the T distribution, and I'll even underline that a lot. Okay, so a lot of people are kind of thrown off because we do introduce the Z distribution first. Yes, that's to introduce the concepts and just kind of the idea and to show you that, hey, you know what's going on here because you know how a Z distribution works. But in terms of what you'll be doing in real life, if there's anything that you're going to use from this course, it's a t-test. And that is when we do a hypothesis test with the T distribution. That's what we call a t-test. And so that is something that you will use or see at some point in your life, I promise. And so for us, right, what I want you to remember is that, okay, well, for real life applications, we should use a T distribution. And so make that your default, even though we're just introducing it now after the Z distribution, but kind of put that to the side, take the skills that you learned, right, about hypothesis testing and confidence intervals, and now apply it to the T distribution. And so for this reason, if you are unsure of whether to use a Z or a T distribution slash Z or T test, use a T test. Okay. Even though it's kind of newer and whatever, but if you're ever unsure, then make the T test your default. Okay. Good. So there are some assumptions, and we're just going to talk about them. So I'm going to see if I can just grab them all here. Got them. Got to catch them all. For t-tests, or for t-tests, I regret nothing. For t-tests, I'm not going to make you check assumptions, mostly because they're all they're always going to be satisfied. But also, even if they're not, then we're kind of okay anyways. And I know that's kind of bad, but it's only because I want you to save your assumptions energy for chapter 6 when we actually do need to check assumptions. So technically, yeah, I'm being lazy and not checking assumptions so thoroughly for t-tests, but, and we should be. And of course, if you're conducting a study, then you should be checking assumptions first. But like I said, usually they check out and it's not really an issue. Whereas for proportions later in chapter 6, it will be really important, and I will give you marks for checking the assumptions. So anyway, so let's talk about these famed assumptions are. So we can apply a t distribution as long as observations are independent. Okay, and so we've had this independence assumption before, or we've kind of seen it before, and it's really just, can we assume that each observation in our sample is independent of all the others? And so one way that we can ensure that is, of course, a random sample, which is kind of assumption number 2. But the second way that we can ensure that is that the population has to be a lot larger than the sample. And I know you're thinking, hey, Emily, you just spent so much time telling us, oh yeah, bigger samples, bigger samples, bigger, but not too big. Okay, because as soon as you start taking up too much of the population, you are going to have some dependent observations, right? Because if you've taken up too much of the population, then you're going to have, big chunks of the same family, for example, and that sort of thing, and then you lose that independence assumption. Usually it's really hard to take a huge chunk of the population, and so it's not really a concern. But typically you should make sure that your population is at least 20 times as large as your sample, but usually that's fine, especially if you're sampling in Canada, then it's going to be hard to sample more than I don't know, 10% of the population. That's huge. So your data, of course, has to be random, right? Randomly selected. So if you're collecting a sample, it has to be randomly selected, or you might be doing experiments, and then of course it should be a randomized experiment. The normal distribution, so the population has to have a normal distribution. And then, but this isn't even that strict, because in practice, it's enough for the distribution to be symmetric and single peaked, right? Usually we're looking for that nice bell shape, right? But as long as it's kind of symmetric and single peaked, then we're okay. And we can kind of say, yeah, it follows a normal distribution, unless the sample is very, very small, right? And so as long as it's not extremely skewed, then you should be okay. So we talked about the central limit theorem in chapter 4. And so what that said, remember, it might be a nice refresher here. The central limit theorem says that regardless of the distribution that you're sampling from, right, then as long as your sample size is large enough, the distribution of the means is going to follow approximately a normal distribution. And so sampling distributions will be nearly normal as long as the sample size is large enough. Okay. We do run into some trouble with small data sets. I'm not going to get into it too much, but so the central limit theorem really only works for large samples. Remember, we're kind of using sample sizes larger than 30 as kind of good enough. So for smaller sample sizes, you'd have to just look at the distribution. Does it look normal? So again, kind of more caution. We should exercise caution when verifying the normality condition for small samples, right? And so even if you look at your data, right, and you can justify it following a normal distribution, if you are looking at things like income data is notoriously skewed. House prices, as soon as it has to do with money, it seems to be skewed most of the time. And so that's something for you guys to keep in mind, right? Do I expect the distribution where I pulled this data from, do I expect that to follow roughly a normal distribution, or kind of vaguely, do I expect this distribution to be symmetric, right? And am I confident that outliers are rare? Okay. So really this part here just says we need to be careful. Oops. Be careful if the sample size is small. It's basically all it's saying, right? Something like n less than 30, right? We'll consider that small. And then on the plus side, a large sample would ensure that the sampling distribution of the mean is nearly normal, right? From the central limit theorem. And if we have a large sample, then the estimate of the standard error, S over root n, notice that we've replaced sigma with S now. But even then, as long as we have a large sample size, then S over root n is reliable, meaning it's nearly as reliable as sigma over root n. Okay. Let me just get sorted here. Okay, all cleaned up. All right, for now. Okay, so let's talk about the t distribution. So there are a couple of facts that we need to keep in mind, and a lot of them are the same as the z distribution. So the t distribution is always centered at 0, right? Just like the standard normal z distribution. I don't remember if I've called it the standard normal before, but that's another way. I call it z, just to kind of point you in the right direction, but it is called the standard normal distribution as well. Z is. The t distribution also has a bell shape, but what happens is that the tails are thicker than the normal models, and there's a little kind of illustration here, right? So what happens is that because we've got this variability in S as well as the mean, remember the area under the curve is the probability of something happening. So if we lift up these tails, right, and we're making more room out here, we're making more room for we're increasing the probability of these values happening further out into the tails, right? That's what's going on. And so it kind of gets, so from the Z distribution, if the Z distribution looks like this, the T distribution kind of like smushes down like this, right? And so it still has that same shape, except now the T distribution is this solid blue line here, or the colors didn't come up too nicely, but right, so we've got this solid line, and that's the T distribution, and it just makes a little bit more room in the tails. So we say that they are thicker, right? Therefore, observations are more likely to fall beyond 2 standard deviations from the mean, or rather standard errors from the mean. I guess I could change that. The irony is not lost on me. Error replaced with error. Right, so we have that 2, so a Z of 2 or kind of beyond 2 as a flag. Okay, this might be considered extreme and we might end up rejecting the null hypothesis. So now we're still going to use that 2 as a guideline, but if we have a small sample size, then 2 is not going to be that big of a deal, right? We would need something quite a bit larger, but so these extra thick tails are helpful because now if we have a small sample size, then all we do is kind of make room in the tails and say, okay, well, my sample size is not, very reliable in terms of looking like the population. So yeah, we'll just allow for more extreme values. But at some point, right, it's going to start to close off again, just like the Z distribution. But it's just staying kind of up a little higher for a little bit longer and then closing off, but never actually closing, right? So the shape, and this is the tricky part with the T distribution, the T distribution, the shape of it, how much room is in this tail, in the tails, depends on the sample size. And so that leads us to the degrees of freedom. Sounds cool, right? So because the T distribution has thicker tails for small sample sizes, and then what happens is that as your sample size increases, then the T distribution starts to approach the normal distribution or the Z distribution. If we think about that for a little bit, well, the only difference between a T and a Z is one, Z uses the population standard deviation and one uses the sample standard deviation, right? But if I'm calculating the sample standard deviation of a large enough sample size, so as I increase my sample size, that sample standard deviation is getting closer and closer and closer to the population standard deviation. So that's why eventually it'll start to look like the Z distribution. It just depends on your sample size. So as the sample size increases, the T distribution approaches the Z distribution. So it's kind of fun. And it doesn't actually take long. We don't need huge sample sizes for that to happen. But how can we communicate our sample size to the T distribution? Well, so like I said, that's when we use the degrees of freedom. So the degrees of freedom are how we communicate the sample size to the T distribution. Okay. And just as a little example, so you know what I mean by that, it's nothing crazy. It's just going to be, so for a single sample, right? So so this is really going to be for a one sample mean sigma unknown problem, then our degrees of freedom are just going to be n minus 1. It's just the sample size minus 1. And what you'll see here is that, and I also included the formula sheet, right? This section from the formula sheet. And we're going to walk through a hypothesis test and confidence interval, but hopefully that doesn't feel too bad, right? This should look very and feel very familiar from chapter 4, right? But I do want to show you that here it is on your formula sheet, right? So whenever you need the degrees of freedom because you've calculated a t, I'm going to tell you how to find the degrees of freedom, right? And so that's not really going to be an issue, but it's just something that we need to remember. For a t distribution, we need to know the degrees of freedom. So here, I keep forgetting that these are not color-coded, very confusing. But so this, the darkest line is the Z distribution, right? And so the Z distribution is the normal. And then here, the lightest color is when we have degrees of freedom equal to 1. So we have 1 degree of freedom, which means what? It means our sample size was 2. Well, yeah, we are expecting it to be kind of, well, we don't really know. This is not representative of our population. We don't really know what's what. So, so it's making lots of room for probabilities happening far out in the tails. But then what you see is we've only gone up to 10 degrees of freedom. But what you're noticing here, hopefully, I shouldn't tell you what you're noticing, but what we're seeing here is it quickly approaches the Z distribution, right? The normal distribution. And so even with a sample size of 11, right? 10 degrees of freedom is from 11 minus 1. We're basically looking at the Z distribution, right? And so what happens to the shape of the t distribution as the degrees of freedom increases? Well, it approaches the normal distribution or the Z distribution. Okay. So the degrees of freedom dictate the shape of the t distribution, right? Is it going to have lots of room in the tails, or is it going to be very similar to the Z distribution? And because the t distribution only relies on the degrees of freedom to know everything about it, we say that the t distribution only has one parameter, and that parameter is the degrees of freedom. Okay. Oy. The t distribution only requires the degrees of freedom, and usually I'll abbreviate degrees of freedom as DF. I think I did it in the text, but I'll do it here too. Okay. So it only requires the degrees of freedom to determine the shape. Determine the shape. So we say the t distribution has one parameter. Has one parameter. The degrees of freedom is that one parameter. Okay. I only mention that because I'm pretty sure it's on a quiz somewhere. Worth mentioning. Okay. Great. Let me just get rid of some of this here. Okay. Okay. So one of the main things that changes is that instead of using the Z table, of course, because we're not calculating Zs anymore, we're calculating Ts, we have to use the T table. Now, we've seen the T table before, blah, blah. We've seen it already when we had to, or we didn't have to, we used it to find Z stars, right? The critical values for confidence intervals that we built in chapter 4. Now, we're going to use it, and in fact, we end up using it kind of in the same way for T's. It's just got that added layer of the degrees of freedom, which is that middle section that I said, don't look, just kind of ignore that for now. Now we're going to look at it. Okay. So a little bit different, and I think it might be helpful, and man, I wish I had thought of it before arranging all my cutouts so that they fit nicely on a page. But let's go to the T table. So go to your tables, and it's table C. So the T table has the confidence levels up here at the top, right? It has the degrees of freedom in the left-hand margin. And so you can pick your degrees of freedom. Remember, the degrees of freedom is your sample size -1, which is not going to change. So what happens with the T table is once you've found your degrees of freedom, let's say, for simplicity's sake, let's say you have 10 degrees of freedom. Then this row is the only row that you can look at. You can't jump around. So it's different from the Z table in many ways. It does sort of the same thing. It gives you the area and the tail, but it behaves very differently. So once you have your degrees of freedom, then that's the line that you have to stay on. Okay, and then you ignore everything else. Okay? And so spoiler alert, if you want a T star, right? And I'm like getting way ahead of myself, but I just want to show you that we already know how to do this. If you want a T star for a 95% confidence interval, well, you find 95% here, and then your T star is what? 2.228, right? So we're going to use it the same way that we did use it for finding Z stars, right? Z star is basically a T with infinite degrees of freedom, right? Because it's the entire population. So what's different though is that these values here, these are T values. And notice that they're only positives. Because it's symmetric, just for simplicity's sake, instead of having a positive side and a negative side that do the same thing, what it's done is it says, okay, well, here are the positive values, and find what you're looking for by taking the absolute value of your calculated test statistic. And then what we do is we try to place it along this line. So we try to figure out where it would fit within these T's. So it's less precise than the Z or the Z table, but I think you're gonna like it more once you kind of get the hang of it, because it is so, it's kind of like simpler to use. So what you do is you calculate your T, and then you try to find where it would fall in between. So let's say it falls between these two values here, just for illustration. So what you do then is you have to know if you're looking for a one-sided p-value or a two-sided p-value. And remember, that goes back to the alternative hypothesis. If you have a not equal to in your alternative hypothesis, then you have a two-sided test. Otherwise, you have a one-sided test. And then what you do is you kind of like take your two fingers and you run them down here, right? And then let's say we have a one-sided test. So then our p-value, our one-sided p-value is between 0.025 and 0.05. Okay, so I've got that all written out, but sometimes it's nice to just show you what I mean so that it doesn't look so scary. But one thing to keep in mind is that p-values, they're the areas in the tail, right? So as we move, and t behaves the same way, starting at 0, it's centered on 0, right? And as we move further and further out, we move further out into the tails. So of course, the area in the tail for 2.228 is going to be less than the area in the tail for 1.812, right? And so you want to be careful when you read these p-values, you read them from right to left, right? Just make sure that you're giving them from smallest to largest. Okay, let me just bring this in so that we can, I've got a better idea. Okay. I will bring it in with that highlight there, but let's just go through these steps here. So I did go through a little bit more if you want a refresher on the p-value, because it is kind of raw, right? And so it's okay, p-values are scary, no one really knows what they are, everyone thinks everyone else does, but no one does, and it's okay, you will get the hang of it. And so right, and also a note here that notice that there are only positive values of t in the t-table. So if you calculate a negative t-score, then you have to use the absolute value. And I've got the absolute value here, but it's really just dropping the negative, right? So here's what we were just going through. So to find the p-value of a t-score, so a test statistic, a t-test statistic, we follow these steps. So you have to calculate your degrees of freedom, right? N-1 for one sample. And then in the left-hand column, you're going to find your degrees of freedom. You can't stray from this row. Usually that's not something people have a problem with. So moving on. So then you move along that row to figure out where your calculated t from step 2 would fall. Okay. And then once you've found the two values that surround your calculated t, you should record them, right? So because you have to show your work, you should record them like this. So, and we're going to do an example. So I always like to put my calculated t in absolute values in the center, and then I put my bounds that I've found around it. Okay, so you're going to have your lower t and your upper t. And then you can go back to the table. And so now you're going to have your two fingers on two values that wrap around your calculated t. And now you're going to follow these columns down to the bottom of the table, right, where those p-values are. So then from the alternative hypothesis, you'll know if you have a one-sided or a two-sided test, right? That's going to determine if you need a one-sided or two-sided p-value. So now you're going to have a range for your one-sided or your two-sided p-value. And here I've got a note, read from right to left as the p-values are decreasing as you move further into the tails. All of this I said. So depending on what you preferred, kind of visual or written, you've got it all. And then you're going to record the range of the p-values you found, right? So your p-value is going to be between two values. And you can still compare the range. It's going to feel weird in the beginning, but if you know that the alpha level is between, if the alpha level is 0.05 and your p-value is between 0.01 and 0.05, then the highest it can be is 0.05. So even if you're on the alpha level, you can still figure out how your p-value, because remember the p-value is somewhere in between those. It's neither of them exactly, it's somewhere in between them. So you can still figure out how your p-value relates to the alpha level. Now I'm going to crop top this, and then I'm going to bring in a little excerpt of the t-table. Let me just bring it in. Okay, so I did the same thing where I kind of, it continues on, but I cut it up. So let's just pretend. So say we have degrees of freedom equal to 10, and our t that we calculated was, just for the practice, negative 1.974. Just making up numbers here. So then what we do is we take just the positive version, 1.974, and then what we found was that if we go along here, right, and t's are increasing as we move out further into the tails, and so we found that the calculated t was between 1.812 and 2.228. I'm just pretending here just to show you what this would look like. So what we would say is, using degrees of freedom equal to 10, we find because this would be part of the work that you're showing, right? You're telling me what you are doing. So we find that the absolute value of t equal to negative 1.974, make sure, so absolute value you show by doing two vertical bars around the value. We find that that is between 1.812 and 2.228. Okay, so it's somewhere in here. This is a good time to make sure that what you're saying makes sense. Sometimes one mistake that I see, I'll say often, is you tell me that 1.97 is between 1.09 and 1.3. No, it's not, right? And so you just want to double check, make sure it makes sense. So from here, right, how do I show in my work how to find the p-value? So the p-value, and I'll say one-sided because this is just a made-up example, is somewhere between what and what? Well, I'm going down here and going down here. So my p-value is somewhere between 0.025 and 0.05. Okay. Let's think about this for a second. So what we're saying is that this p-value, the one-sided p-value, even though we don't have a value for it yet, or we won't unless we use software. So because despite not having an exact value here, there we go, we still know what we need to know about the p-value. It's somewhere between 0.025 and 0.05. So is that less than 0.05? Yes, it is, because 0.05 is at the upper end, right? And we're saying, well, it's somewhere between 0.025 and 0.05. So even when we know what it kind of where it falls, we can still use that to compare it to the alpha level. It's just a little different. One thing that I can't remember if I mentioned, it would have been, where is it? Where did I put it? Oh, here it is. Time to move on, I guess. Okay, so this is how you would show your work. This is how to show your work for finding the p-value. Okay, when using the t-table. All right, so I've snuck it into some general things to keep in mind when using the t-table. So t-scores have to be given to at least 3 decimal places. Why is that? Well, just like we rounded z to 2 decimal places to match the table, now t's get rounded to at least 3 decimal places. We can go for more in this case because, why? Because these have 3 decimal places. Right, so you don't want to round too much and have it kind of fall between the cracks here. But so at least 3 decimal places, but you can have more and still place it somewhere on the line, right? And so that's one thing. So you want at least 3 decimal places to match the t-table. Here's the thing that happens, okay? If your degrees of freedom aren't on the table, you have to use the closest degrees of freedom rounding down, okay? So why is that? Well, the degrees of freedom are kind of the sample size, essentially, right? So if you were to round up, then you would be saying that your sample size is larger than it actually is. And that's really bad, right? Because then you would be misleading people into thinking that your results are more reliable than they actually are. So that would be really bad. And so even if it hurts, and I'll show you an example on the t-table. Let's go to the t-table and I'll show you. So notice we're fine and dandy here up until 30 degrees of freedom. After 30 degrees of freedom, it starts kind of increasing. So it goes from 30 to 40, 40 to 50, 60, 80, 100, from 100 to 1,000, yikes. So even if you had a sample size of 900, well, you would have to use 100 degrees of freedom. For some reason it hurts. I don't know. I can't explain it, but for some reason it's like, oh, you feel so cheated. But don't worry, because if you look at these values, look at how similar they are, right, as you move. So there's really no difference, but it just feels weird to go for 100 degrees of freedom, even if you have a sample size of 900 or something crazy. Right, and so I do want to highlight this because it's going to come up and I will get questions about it. And maybe if I do this, I won't. No, I will, but it's okay. By rounding down. And that's actually something that I take marks off for. She wouldn't. She would. Not a lot of marks, but I would take off maybe 0.25 out of 10 if you use the wrong degrees of freedom. Actually, I know that's what I take off. I don't know why I was being all, oh, maybe. But anyways, so you have to round down, and I do set it up so that I make you do that. I know, rude, right? Another thing, or another 2 things, I guess, that come up a lot is, what if our t-score is kind of beyond the range of the table, right? So let's say we have 20 degrees of freedom and we calculate our t to be 4.976. So then if we go to our table and we have 20 degrees of freedom now, and we calculated 4.9 something, 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 right? That's okay. The t's keep going forever as well. They go till infinity as well as the z's. So that can happen. It just means that the p-value is going to be really, 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 really small. In fact, it's going to be smaller than, depending on if you have a 1 or 2-sided p-value, it's going to be smaller than this. Same thing on the other end of the spectrum, right? If you're close to 0 here, then your p-value is going to be larger than these 2, right? So I've got that illustrated here, how I show that. So if the t is, and maybe what I should do, let's rearrange this so that we follow the same 3.850. Okay. Just so I'm always writing it the same way. Yeah, now it follows through. Okay. So then the one-sided p-value is less than 0.0005 in that scenario. Or if you have a calculated value of 0.532 and 20 degrees of freedom, right, then that's going to be closer to 0 than 0.687. So the one-sided p-value is larger than 0.25. Okay. Lab 5, the Lab 5 solutions use, where can I sneak this here? Maybe I'll just mention it and show it to you because I have it written at the top of Lab 5. But I just want to show you. Where is it? Uh-oh, I might just need to take a little moment to bring it in. Hang on. Okay, so Lab 5 uses this tables 2, which I've also posted and I've marked it as optional. And these are actually the tables that come with the textbook that we're using. I know, you almost forgot that you have a textbook, right? So, I don't know, I'm just joshing. So I don't love these tables. That's why I use tables from a different textbook that have the lines, and I just find that they're easier to read. But I do want to point out some differences here. So this is their Z table. The Z table is the exact same as what we've been looking at and using. It just, I just find it doesn't look as nice, but maybe I'm just being grumpy about it. I don't know. So Z table, and then so here, B2 is the T probability table. So this is the T table that they have. And what we see is that, okay, so the P values are up here above. And there are lots of different ways that you could structure these tables, and you might come across some more tables. But just remember, if you've kind of dissected one, you kind of know what's going on, and you can figure out what's going on in a different one, just like this. So it has the p-values up top, right? Whereas we have the confidence levels up top, and then it has the degrees of freedom going past 30. And then it stops at 500, and then infinity is what Z star is. So it requires you to know that infinite degrees of freedom is Z star. And notice that it only has 1, 2, 3, 4, 5 cutoffs, right? Whereas we have quite a few more. Can't remember how many, doesn't matter. And another big difference is that it only has 2 decimal places, whereas we have 3. So I prefer our table. That's the one that the solutions to the quizzes and the tests are programmed to. So to match, so you should use those ones. But just be aware that this is here if you wanted it. And for Lab 5, it uses this T table, but it's the same. It's just has more yet less information at the same time. Weird, right? More degrees of freedom, but less information in here. I don't know. Okay. So we've talked about what happens if your T is kind of off the table, off the charts. And we also already looked at how do we find these critical values. So for a confidence interval, we're going to need a critical value because that's what dictates how confident, or the confidence level of our confidence interval. So to find a T star, we do the same thing that we did for a Z star, which we already saw. So you have to find the confidence level that you want in the top row of the table, and then you need to know your degrees of freedom, and then you drop down just to your degrees of freedom line. Okay. And hopefully that feels okay. That's all there is to it. Okay. And we will go through and do a confidence interval, and maybe I should have saved this for then, but here I'm just introducing everything that you need to know about the t-table and the t-distribution. And I think we're ready to actually start talking about one sample means with the t-distribution. With the t-distribution is really just saying this means sigma unknown. Right? Because we're now using the sample standard deviation instead of the population standard deviation. So setting the scene here, when we've collected one sample of numerical data, we use the mean and the standard deviation of the sample to infer something about the population mean, right? We're trying to learn about the population mean, and we're using the sample information to do that. So let's walk through the steps for hypothesis testing for one sample mean sigma unknown. Okay, as we move through here, I'm going to talk about question types. And so one sample mean sigma known is the first question type that we introduced in chapter 4. But now we're going to start talking about one sample mean sigma unknown. And the question types are they're blocked in the formula sheet, right? And so that's how I refer to them. And potentially the hardest part, especially on the final exam, when you have to read a bunch of questions and they're often not in order, right? Then reading a question, and the first thing you have to do is figure out what type of question is it. Once you know what type of question you have, then that puts you in the right section of the formula sheet, and then you can't move from there, and then you've committed, and after that it becomes hopefully quite easy to work through. But deciding the type is very difficult. So you have to read a problem, decide what type it is. And so whenever you're reading a question, I want you to kind of argue with yourself what type of question you think it is, right? Because that's how you know how to solve it. So very similar, wow, it was not in pointer mode here. Okay, very similar steps that we developed in chapter 4. And that's why we did that, just so we'd have that kind of groundwork done. Can you imagine introducing all of hypothesis testing now? We just talked about the t-distribution for who knows how long. But anyways, so the steps are: 1, you have to state your hypotheses, right? So H naught is that mu equals mu naught. So nothing has changed here. The default is not equal to, but it depends on the question for the alternative hypothesis. And still mu naught is a placeholder for a number. For the number, we want to compare the sample mean to. Okay, so that's still the case. Step 2, do the test, do the do. The test statistic that we calculate is going to be a t, right? But how we calculate it, it really doesn't change. It's just our S, our sample standard deviation, is being used instead of our population standard deviation. But the calculation stays the same, right? Step 3, find the p-value. That's when you use this setup that we kind of went through a fake scenario of. Wow, sorry, it's catching up. This setup here. Right, so this is how you show your work for step 3, finding the p-value. And really all we need is our degrees of freedom, how many degrees of freedom we have. And for one sample, the degrees of freedom is n-1. But again, that's on your formula sheet, right? So nothing crazy. For your conclusion, right, as soon as you have a p-value, then everything stays the same. So how you get that p-value might change, but how you use the p-value stays the same. So we can draw our conclusion based on how the p-value compares to the alpha level, just as before. So this is the exact same. It's just a little reminder of what our decision tree here. So if the p-value is less than the alpha level, so if it's small enough, we have enough evidence to reject H0 in favor of HA. And if the p-value is not less than the alpha level, then we do not have enough evidence to reject H0. So this is just a reminder. Yeah. Good. Okay. All right. I think we're ready for an example. Let me get set up here. Okay, so our example is going to be from biology, but that's okay. The level of dissolved oxygen, because it actually doesn't matter what we're talking about. And that's the really fun part about stats, is once you kind of know the notes to sing, you can sing most anything. Dun, 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 dun. Anyways, there's no class here to stop me. I can do whatever I want. Once we know the steps for hypothesis testing and confidence intervals, and we know the theory of t-tests and all that kind of fun stuff, it really doesn't matter what the data is about, right? So it can be biology, it can be chemistry, it can be social sciences, it can be business, it can be anything, it doesn't matter. So that's the cool part. So the level of dissolved oxygen in DO, I guess, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. So here are the results in milligrams per liter. So here they all are, 15 locations, randomly selected. So that's good, right? We should look at the distribution of these, but we're just going to jump right ahead and assume that we have a roughly normal distribution and they come from a normal distribution, even though our sample size is pretty small, but that's, we're okay with that. So we're going to move ahead without officially checking those. We're told that the mean and the standard deviation of this sample, right, are, so X bar is 4.771 and S is 0.9396. So here it says that it is S, so it is the sample standard deviation, but just the fact that it says of this sample, then you know that this, whatever standard deviation you have is from the sample. So here's the a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Now, as soon as you see is there evidence, that tells you to do a full hypothesis test, right? Because that's why we use hypothesis testing, is to build evidence, right? So do a full hypothesis test. So it looks kind of like a small problem, but we know hypothesis testing is kind of, you know, this multi-step process. So buckle up. Often I write more around a question than you would need for full marks on written work. So to help you out, everything that you would need to submit in terms of written work, I've boxed up in these little boxes. So here in the solutions, right, I've got everything that you would need to show for full marks for written work. So let's just take a step back here. And okay, so we have our sample mean and we have our sample standard deviation. Okay, so what type of question do we have here? Well, because it's a sample standard deviation, I just have one sample of dissolved oxygen levels. So it's a one sample mean problem sigma unknown. So in terms of the type here, one sample mean sigma unknown. All right. So that's the type that we're dealing with for this example. And no surprise, that's all we have talked about so far in this section. So first thing you have to do is you have to state your null and alternative hypothesis. Now remember, to state your null and alternative hypothesis, you have to figure out what value do you want to compare your sample mean to. So the kind of hot topic here is the 5. So anything below 5 is bad news bears, right? And so this 5, that's the value that we want to compare our sample mean to. And so that's what we use in our null and alternative hypothesis. So here, the null hypothesis is that mu is equal to 5. So we have to assume it is 5 unless we find proof otherwise, right? So if we kind of think about it, well, 4.771 is less than 5, but is it significantly less than 5? That's what we want to know, right? And so that's what we're testing. So this is a one-sided test because we only care about it being less than 5. It doesn't seem to be a concern if it's significantly higher than 5. Really hard / impossible to use a value of 4.771 to prove that it's higher than 5. You can't do that. It would have to be above 5 to be able to prove that. But because we're only concerned with this one extreme, it's a one-sided test, right? So, oh, and I have here, so mu, this mu here is the mean, the population mean for the dissolved oxygen level in the stream, right? Step 2, do the test. And just a reminder what the sample mean and standard deviation are here, but really pretty straightforward stuff. We've practiced this for z-scores and it's the same calculation, so we can just go ahead. Notice that I'm rounding to 3 decimal places because I want it to match the t-table, which has 3 decimal places. And we're using mu. This could be mu naught here, just to emphasize that it's from the null hypothesis, but really, if it just says mu, we assume the null hypothesis is true. So we have to assume H naught is true until we have proof otherwise. And the null hypothesis says that mu equals 5. So if you want to use mu naught or just mu, either way, it's the same thing. Step 3, find the p-value. So we've got a negative value for t, right? So in order to use the t-table, we have to find the absolute value, which is basically dropping the negative. Because the negative really only indicates which side of 0 the t is on. It doesn't, the tails have the same area in them. And we need our degrees of freedom. And I want to see how you found the degrees of freedom. This is not because I don't think that you can do 15 minus 1. I do. But you need to show me that you know all the steps of what you're about to do, right? Show me that you know that you have to find the degrees of freedom and that the degrees of freedom is n minus 1 and your n is 15. 15 minus 1 is 14. So usually I just end up doing the calculation in the sentence. So using the t-table with degrees of freedom equal to n minus 1 equals 15 minus 1 equals 14, we find that the absolute value of t, so notice the setup is the same as what I did in our kind of quick example there. So the absolute value of t, right? And so this is that value here. right? It goes in the middle. So you try to take your calculated t and you place it along the 14 degrees of freedom. So let's go ahead and use the tables. So we have 15 degrees of freedom, 14 degrees of freedom, sorry, and 0.944, I want to see. Yeah, so the absolute value of negative 0.944 is 0.944. So 0.944 would go somewhere in here. So I'm just going to circle these up here. 0.944 would go somewhere in here. And my goal is to find the p-value. So first thing I'm going to do is I'm going to jot these down, right? And that's what I've done. So 0.868 and 1.076, 0.868, 1.076. And then I'm going to trace down, reminding myself that I have a one-sided test, so I need a one-sided p-value. So here we go. Wait. Okay, so I trace down here, and my one-sided p-value is going to end up between, 0.15 and 0.2. Remember to read from right to left here. 0.15 to 0.2, so I jot that down. Unless no, good. I thought my eyes skipped around for a second there. So, which means one-sided p-values between 0.15 and 0.2. Notice the structure here has stayed the same and it will always be the same, right? So once you have figured out the structure, then you can just kind of fill in the blanks, right? Fill in your degrees of freedom, fill in what values wrap around your t, then fill in what values surround your p-value. I've got a little note here. So the t-table is less precise than the z-table, but I guess I'm kind of selling you on the t-table, or trying to, but I think you'll find it more efficient once you get used to it, right? So once you get used to using the t-table, it's really kind of sluggish to go back to the z-table. It's like, oh, all this work. No, I don't wanna. So then for our conclusion, right, we were told to use a 0.05 alpha level. So then first things first, I have to compare my p-value to the alpha level. Is it less than the alpha level, or is it not less than the alpha level? So our p-value is somewhere between 0.15 and 0.2. That's neither of these bounds are less than 0.05. So all I know is that it's somewhere above 0.05. So since our one-sided p-value is between 0.15 and 0.2, here I really like to highlight that from this here, you know what your p-value is, right? So I want you to try to emphasize that you know what the p-value is. It's greater than our alpha of 0.05, which means we do not have enough evidence to reject H naught. Remember, there were three parts to the conclusion. So this is kind of part one. And then your conclusion in terms of H naught is part two, right? Either you have enough evidence to reject H naught or you do not. And then the last one, I'll use pink here, is of course your conclusion in terms of the question. So what does it mean in terms of this question? We were really hoping that we weren't going to reject the null hypothesis. Why? Because then all the fish would be dying, right? That's really bad. So it depends on the scenario. Sometimes you are kind of wanting to reject H naught. Sometimes in cases like this, it's like, okay, yeah, so it's lower than 5, but it's not significantly lower. So we don't have to worry quite yet. So you always want to reformulate the question as an answer, right? And so I think the question was, is there evidence that the mean dissolved oxygen level is less than 5 milligrams per liter? Therefore, we do not have enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. Fish rejoice. Ah. I do have, and I included it here because I think it's really nice to see that all this work, except interpreting the p-value and drawing your conclusion, is done really easily using software. So even if you had to go the very, very longest possible way and enter all these data points, all 15 data points like this, you can use the t.test command and tell it what your hypothesized mu is and what your alternative hypothesis is, and then it just does it for you, right? Kind of longer way, if you wanted to use R as a calculator, you can do that here. But sometimes we don't have the data, then you can just use the PT command. But if you need this, this is really just if you're interested. So here, this is optional R code for anyone interested. R is free, right? So you can download it and check it out. I would say use RStudio. It's a little bit kind of more user friendly, but you have to download R first and then RStudio. But so you can kind of ignore this, right? But I think, yeah, so it gives us our p-value. Like I said, if you want an exact p-value or a better p-value, then you have to use software, right? And so here it tells us 0.819, or sorry, 0.1809, which if we go back to our range, 0.1809 is somewhere between 0.15 and 0.2, right? So, but we were able to get what we needed out of this range, out of this world. Okay, great. All right. So of course, we'll go through more examples, but not in the recording. So let's go to the confidence interval example next. Let me just clean up here. All right. So the confidence interval for sigma unknown, so one sample mean sigma unknown versus sigma known, again, really doesn't change that much, except instead of a Z star, we get a T star, right? So the formula for calculating a confidence interval for one sample mean where sigma is unknown is similar to calculating a confidence interval for one sample mean where sigma is known, simply replacing Z star with T star and sigma with S. And so our formula here looks very similar, right? And so to what we've seen before for Z stars. Reminder that this plus minus chunk is called the margin of error. And maybe I have it here. But to find your T star, right, you need your degrees of freedom, which is n-1. X bar is the sample mean, which is our best guess at what the population mean might be, right? So same idea as before. T star is still the critical value and it's found in the T table. And then again, just like Z star, T star is the only thing that determines the confidence level of our confidence interval. So how wide are these things going to be? S over root n is the standard error of X bar, right? We're used to seeing sigma over root n, but if we don't have sigma, then S over root n is also our standard error. Oh, and I guess I have it here, but T star times S over root n is the margin of error. I realized I forgot to tell you to pause it, but hopefully you kind of let yourself do that anyways. So let's read the question and then I'll give you time, like a moment to pause it and work through it and try to see how much of it you can tackle on your own, and then we'll work through the solutions together. So business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada. Whoa. OSB. Included in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. A study is based on a random sample of 75 reports, right? That's your sample size, from the current year. The average debt, which is defined as the liabilities minus the assets, is $92,172. I don't know why I struggled there. With a standard deviation of a huge standard deviation of $111,538. Okay. Here, although it's not explicit, it is kind of understood that both the mean and the standard deviation came from this sample of 75 reports. Okay. And so that's why this is a one sample mean sigma unknown problem, is because the standard deviation came from the sample. So I want you to construct a 95% confidence interval for the average debt of these companies at the time of filing. Okay, so give it a pause, try it out, and don't forget to interpret the interval. Build the interval, then interpret the interval. But it's the exact same as in chapter 4. So give it a pause and meet me back here. Okay, welcome back. So I've listed the information that we're given here. So we're given that N is 75, X bar is 92,172, and the S is 111,538. So you don't need to show that for marks, but you do need it to solve the problem. So why not? So again, everything in this box you need to show for full marks in terms of your work. So using the t-table with n minus 1 degrees of freedom, which in this case is 75 minus 1, which is 74. If we go to the t-table and try to find 74 degrees of freedom here, let's see here. Then I'm going to go down here 50, 60 to 80, right? There is no 74, and it might be tempting to go for 80, but we have to go for 60. Okay. And how do you show that you did that and you knew to do that? Well, you say, but using 60 degrees of freedom. Okay. We find that T star is an even 2. I gotta see this. Okay, here we go. Back to our tables. So we've got 60 degrees of freedom, and it's just there. Had to zoom out a little bit. And we want a 95% confidence interval. Haha, there it is. A beautiful 2. Happens with 60 degrees of freedom, and only then. Haha, that is just beautiful. So we find our T star is 2 for a confidence level of 95%. So then I set up my empty calculation here, and then I can fill in the numbers. So you go ahead, do the calculations, and make sure you list from lower to upper, right? It gets confusing because there's so many commas, but of course, this comma and this comma are just for readability, right? Whereas this comma separates the lower from the upper. That's only half the marks, right? Then we need to interpret this interval, but we use the same blurb that we used earlier, right? We're 95% confident that the interval from 66,413.40, why not round to 2 decimal places? Money goes to 2 decimal places, so why not? to 117,930, 60 and 60 cents captures the average debt of these companies at the time of filing. I'm pretty sure I just stole that from the question. Construct a 95% confidence interval for the average debt of these companies at the time of filing. Captures the average debt of these companies at the time of filing. Echoes in here. Right, so you just reword the question as an answer. And there you have it. The t-table mastered. So we're going to keep using the t-distribution, but in part 2, we're going to move to talking about 2 samples. And there are kind of different ways that we can have 2 samples. So get excited. All right, see you then.